So today what we're going to be looking at is a kind of a classic mistake that students make when they're first learning how to do derivatives. They run into something where they have the derivative of two functions multiplied together. You can see down here, here's our friend Gottfried Wilhelm von Leibniz. Okay, he's one of the co-inventors of calculus along with Isaac Newton. All right, so when you have two functions multiplied together, the temptation is to simply take the derivative of the one and multiply it by the derivative of the other. We'll actually show that doesn't work, okay? But what we're learning today is called the product rule. Product is the word for multiplication, you guys know that. So if we have two functions and we make up a new function f of x by multiplying those two functions together, then the derivative of f of x is this, okay? Now let's break down this notation here. U is the first function, v is the second function, and this is u prime times v plus u times v prime. In other words, the derivative of the first times the second plus the first function times the derivative of the second. It may be a little bit easier to remember if you simply write it without the of x's parts. It's u prime v plus uv prime. Kind of rolls off the tongue a little easier. Okay? Also, we have this notation using the differential notation here. Dy dx would be du dx times v plus u times dv dx. All right, so just the same notation, or different notation for saying the same thing. Okay? So let's look at why we need this, first of all. Okay? And I'm going to actually use these two as examples. Okay? So if I were to simply take the derivative of this first one, we'll call this u, and we'll call this v, all right? U is the x squared plus 1. V is x plus 1 quantity squared. So what are we going to need to use to find the derivative of v? Chain rule, okay. U prime would equal what in this case? 2x. And v prime, can you do your chain rule without writing it all out?
2x plus 1 times x.
2 times x plus 1 to the first, the outer function is the square, times the 1, which is the derivative of the inside. Okay? So we can, anything times 1 is itself. So it's just 2 times x plus 1. So what students, when they're first starting out, often say is, oh, well, dy dx must just equal 2x times 2 times x plus 1. And we know that that's not the case, because we just saw the product rule. Okay? Now, before today, how would you have found this derivative? Multiply it out. If I actually did multiply this together, it would have been a 4x squared plus 4x.
Wasn't that one of the questions?
Okay? Not exactly.
Something similar to that.
Okay? But let's take a look at this real quick. The x plus 1 squared is x squared plus 2x plus 1. You guys know how to FOIL. And if I multiply that by an x squared plus 1, I get an x to the 4th plus 2x cubed plus an x squared plus 2x plus 1. Okay? Let me make sure I didn't miss anything. Oh wait, plus a 2x squared. Okay? That's what you would get. Well, what's the derivative of that?
4x cubed plus 6x to second plus 4x plus 2.
Does that equal this?
No.
Obviously not. Okay? So there's something wrong here going on, okay? Now this actually is the correct derivative. What's wrong is we didn't use the product rule here. So let's show that this works using what we already have. We would have u prime times v, okay? So the derivative of the first is the 2x times the second function, which is x plus 1 squared. So here's the u prime times the v. We need to add to that u. Well, u is the x squared plus 1 times v prime. Well, v prime, we already said, was 2 times x plus 1. Okay? Now, before you start foiling stuff out, what do you notice here? Okay. Wait, I heard someone say something.
Factor out an x plus one.
Okay, both of those parts have an x plus 1, and they actually both have a 2 in it as well. So I'm going to go ahead and factor out a 2 times the x plus 1, and then what's left over of this first part will be the x and the second of the x plus 1 squared. And what's left of the second half of this is just going to be the x squared plus 1. Okay? So this all simplifies then to 2 times x plus 1 times, that's going to be a 2x squared plus x plus 1, which does not factor. Okay? Now, guess what I would get if I multiplied that whole thing out? I would get this. Okay? So you might say, well, why do we bother with the product rule? Okay. Well, if that were x plus 1 to the 9th, it'd be a whole lot better to not have to FOIL the whole thing out to do it. Okay? Also, as we'll see in our next unit, when we get to actually using these derivatives, this whole unit is just learning the concept and learning the rules, the mechanics of differentiation. Okay? Once we start applying this, one of the most common things we're going to be doing with these is setting the derivative equal to 0 and solving it. And you know, polynomials equal to 0, you want to try to factor. So leaving it in a factored form, like we have over here, is going to be what we want. Okay? So, but this is just a little kind of example of how the product rule is super useful. We don't have to FOIL things out. We can just figure it out, and then our final answer would be right here.
I'm still a little confused with how you factored out 2 times x plus 1.
Well, if you look at our factors here, when I get to here, I have the plus sign in the middle, so I have two parts to this. Both of these have a 2. It's all multiplied together, right, on the two parts? You can't see that. Let me get a better color to highlight with. Okay. So they both have a 2 in common, and they both have an x plus 1 in common.
Okay.
Now the first half happens to have 2 of them. That's why there's one left over in the parentheses here. Okay? But I took out the 2 and the x plus 1 right there.
Yeah.
Okay?
Thank you. Sorry, I was just a little confused.
No, it's okay. By the way, a little rule of thumb, anytime you use the chain rule inside the product rule like we just did, you're going to be able to do something. You're going to be able to factor out something like this. It happens every time. Okay? So that's kind of a cool thing to remember, especially as you then go to simplifying stuff. Okay? There we go. All right, so let's without foiling and confirming, let's go ahead and do this example here. First of all, what is u?
X plus 1.
X plus 1. So u prime is 1. All right. What is v in this case?
X plus 2 to the 1 half.
X to the 1 half plus 2.
Oh, sorry.
Okay, yeah, that's all right. X to the 1 half plus 2, or the radical x plus 2 is the v part. Okay? Especially as you get more comfortable, maybe just writing u and v over that, that'll save you a little writing. But over on the right hand side we have v prime that we're going to write down. And what is v prime?
1 half x. So that would be 1 over 2x. 2 radical x, I guess.
Yeah, so this is 1 over 2 root x. Okay?
Should we try to get the root up top? Or?
No, you don't need to rationalize. That's fine. Okay? So, again, dy dx, we have u prime times v plus u times v prime. U prime is 1, v is radical x plus 2, plus u is x plus 1. V prime, we just said, is 1 over 2 root x. Okay? Now, one of the questions here is simplifying, all right? Because we're eventually going to be solving these, if it's a case like up here where you can pull out a common factor and have it in a factored form, I want you to do that. Here, there's nothing to factor out, but there is simplifying that can be done. Go ahead and distribute. So we have an x, radical x plus 2 plus, and then we distribute this in. So the second half is easy, 1 over 2 root x. But what's 1 over 2 root x times x? The x would be over the root x. X over 2 root x. What does that simplify to?
X plus 1 over 2. Aren't they the same denominator?
Oh, you could combine like terms on that. You could. I'm actually going to go a little different route. Go ahead and reduce this. How does that fraction reduce?
X and x 1 half.
So it's X is...
So it's just radical x on top, yeah.
Yeah, it would be a half of a radical x. Okay, because this is x to the first, that's x to the 1 half. You subtract when you're dividing. Okay, so it'd be x to the 1 half left over. So it's radical x plus 2 plus the 1 half radical x plus 1 over 2 root x. So now we can put these two parts together. And we get 3 halves root x plus 2 plus 1 over 2 root x. Okay? So in these you should go ahead and distribute and simplify as much as you can. Okay? Again, we're preparing to be able to apply this later, and this is the best way to go about doing that. Okay? Again, the rule itself is relatively simple. U prime v plus uv prime. It's a matter of just practicing using it. Okay? Let's do a couple more here. All right? Yes?
Why did you?
Okay, try this first one here by yourself. Okay? I'll give you a minute or two here to work it through. Alright, so I still have the screen frozen here so you can't see. But what did you guys get for, what is u? X squared plus x plus 1, okay? And v was the x minus 1. So what's u prime?
2x plus 1.
2x plus 1. Okay, the derivative of that first half there is 2x plus 1. What's v prime? 1. Okay, so when you do u prime v plus uv prime, you need to do some foiling and combining of like terms, but what do you end up with at the end? 3x squared. Just a 3x squared is what you should end up with at the very end. Now, by the way, this is the factored form of something. Do you guys remember? Does that look familiar?
Yeah. Oh, is it? It's, we've seen it before, but I don't know.
It's the difference of,
A square.
not a square,
No idea.
because that would be conjugates. It's a difference of cubes.
Yeah.
This actually is
Indirectly.
x cubed minus 1.
Yeah.
What's the derivative of x cubed minus 1?
3x squared.
3x
So
squared.
we could have just done
Da
that.
da da da. Okay?
Could we
So.
have just done that?
Wait, then how did you get the wrong answer the first time?
Huh?
Or, like, just change.
Wait, didn't you get the wrong answer the first time?
Oh.
Could we do that?
Where'd it go? There we go. What?
Could we just write like an arrow of x cubed minus 1 and then?
If you recognize that, sure. Unless I specifically told you use the product rule, but the reality is here, guys. That's the beauty of all this. A lot of these have more than one way that you could actually find the derivative. Okay? Some of them there is only one way. You've got to use whatever. But in this case, yeah, you could multiply it together if you recognize that as, oh, that was my difference of cubes formula. For x cubed minus 1, you could go ahead and do it a little bit faster. But again, that's all a matter of what do you see. If you just see a product, then do the product rule and you've got it. If you happen to see something making a connection with the pre-calculus that you've done in the past, and it saves you some time, great, okay? Now, this one down at the bottom here can get really ugly, or it can be pretty elegant, okay? So let's look at this one. The u in this case is just x. The v is the x to the 7th plus 15 cubed. All right, so let's look at this. U prime actually will just equal 1. The v prime, we got to use chain rule, right?
Yeah, so 3 times.
So 3 something squared,
Yeah.
and the something stays the same, times the derivative of it. So times 7x to the 6th. Okay? So this is simply 21x to the 6th times x to the 7th plus 15 squared. Okay?
So what's your trick?
So now, if I'm doing the derivative, u prime times v, x to the 7th plus 15 cubed, plus u times v prime, 21x to the 6th times x to the 7th plus 15 squared. This goes back to what I said on the previous problem. Anytime
Oh, actually,
you do the chain rule inside the product rule, or quotient rule later, you've got a common factor, right? We've got a common factor in this case of the x to the 7th plus 15 squared. Okay?
So you take that out.
So I'm going to take that out. All right? So x to the 7th plus 15 squared was my common factor. What's left over after I do that? Well, in the first one, the 1, and the third of these x to the 7th plus 15s. Okay? So it's just 1 times x to the 7th plus 15. What's left over on the second part? It's a plus 21x to the 7th. Okay? So this whole thing here is going there. The third of these is going here as the leftovers. Okay? So now, and this is where I said this is very elegant if you see it. It's actually very simple, very elegant if you see it. it's just x to the 7th plus 15 squared times a 22x to the 7th plus 15. And that's it. There's no foiling involved. Do not multiply that out. Okay?
Why not?
Hey,
Bless you.
thank you.
So, could you have cubed this from the beginning and distributed the x and done power rule? Sure. Is that a waste of time? Yes. Okay? So don't do that. Okay?
Okey-doke.
Let's do a couple more practice. I'm not going to do all of these because the rest of these will just be your own practice for homework, okay? So pick one. What one do you want to do?
Can we do the bottom one?
Sure. All right. So u is the x to the 7th. V is this. So what's u prime?
The x to the 6th.
7x to the 6th. What is v prime? Gotta be careful with this one.
4x squared plus 7 all to the half.
No.
That's what it is currently. 4x squared plus 7.
I'm sorry, I'm doing different things.
It ends up being, 4x over 4x squared plus 7.
Okay, it actually does because we do 1/2 times 4x squared plus 7 to the negative 1/2. There's the outer function. The derivative of something to the half is 1/2 something to the negative half.
So it's 1 over 2
Okay.
times 1.
Yeah. And then we got to multiply by the derivative of the inside. We're doing the chain rule. So the derivative of the inside is that 8x. Okay? If we simplify here, we've got 4x over the radical 4x squared plus 7. And again, I don't care if you leave that as the 1/2 power or put it in the radical, but do put it in the denominator. Okay? So, now we've got a product rule. dy dx u prime 7x to the 6th times v. I'm going to use the radical. Radical 4x squared plus 7 plus the u times v prime 4x over radical 4x squared plus 7. Now, this is something I want you to do because it will make life a whole lot easier in the future. You can think of this as factoring out, or you can think of it simply as getting a common denominator. But I do want you see how we have this radical 4x squared plus 7 in common, but one of them has it in the numerator, one of them has it in the denominator. Okay? What we're going to do is actually multiply this first half so that we get the radical 4x squared plus 7 as a denominator, but I've got to multiply the top by a radical 4x squared plus 7. So this is going to square the radical, right? Does that make sense?
Yeah.
Why only the radical? Why not 7x to the 6?
Well, because I'm multiplying by radical 4x squared plus 7 over radical 4x squared plus 7. Okay? This is what we're doing. Radical 4x squared plus 7 over radical 4x squared plus 7. That's what we're multiplying that by. Okay? So that's going to square the radical on the top and put a radical in the denominator. Okay? Now that looks a little nasty, but here's why we're doing this, okay? When I do that, I've got a common denominator, so this whole thing is going to be over a radical 4x squared plus 7. the numerator is going to be 7x to the 6th times now a 4x squared plus 7 to the first power plus a 4x to the 8th power. And look at what ends up happening. When I distribute, I have a 28x to the 8th. So 28x to the 8th plus 4x to the 8th is a 32x to the 8th. And then I distribute this here, plus a 49x to the 6th. And that's over the radical 4x squared plus 7. Okay? Now, believe it or not, that is a much simpler and a much more useful form of this answer. Okay? And in fact, if we went one step further, it would be even more useful, because what do you notice about the numerator?
Take out x to the 6th.
We could factor that a little bit. X to the 6th times 32x squared plus 49 all over the radical. Now remember what I told you our goal was here. When we start applying this, we're going to be setting this equal to 0 and solving. So getting it into a form like this now sets us up to where if this equals 0, I know, oh, well, x to the 6th is 0, so x is 0. Or the 32x squared plus 49 is 0, and I get an imaginary number. Plus or minus 7i over radical 32. But, you know, we're setting ourselves up for success in the future. I want to show you, though, an alternative form of simplifying this, and whatever way makes the most sense to you, I want you to use that. Okay? You can think of this as getting a common denominator, or going back, dy dx is the 7x to the 6th radical. Well, in this case, I'm thinking of it as 1/2 powers. Okay? Plus, and I'm going to put that together, 4x to the 8th times 4x squared plus 7 to the negative 1/2. Okay? Now, in this sense, we're thinking of it rather than as getting a common denominator, I'm going to think of it as factoring. Okay? And what I'm going to do is I'm actually going to factor out, and this is going to seem weird, but I'm going to factor out the x to the 6th, but I'm also going to factor out a 4x squared plus 7 to the lower power. Which one is the lower power? The negative 1/2 power. Now you've probably never really worked with factoring out negative exponents before. But check out what happens here. The right hand side is pretty easy because I took this whole thing out and I took out an x to the 6th, so it's 4x squared left over. Okay? The challenging part is to notice what happens with this when I take out a negative 1/2 power. Well, think of it, if I distribute it back in, I want to end up with a positive 1/2. So negative 1/2 plus what gives me a positive 1/2? Just 1. So notice the 4x squared plus 7 is now to the first power. And I took out to the x to the 6th, so there's my 7. Okay? So notice, if I were to multiply this back together, this to the negative 1/2 times this to the first would be 1 minus 1/2. Gets me back to the 1/2 I had originally. Okay? But notice where I end up with this one. I distribute, I get a 28x squared plus 49 plus a 4x squared. This is x to the 6th over the 4x squared plus 7 to the 1/2, or square rooted. And what is in the brackets? Well, it's that 32x squared plus 49. And when I put it all together, it ends up being exactly what we got the first time. It's just our path to get there was a little bit different. Okay? Some people look at the factoring and that is totally foreign to them and it makes no sense, so they like the common denominator method. Other people like the factoring and hate the common denominator. So whichever one makes sense to you, do it that way. Alright, so I've given you a few more examples just for practice. Okay? And you can work through those with the rest of the time we've got and finish these up for homework. Not too many of them, but enough to give you some good practice. On Monday, we're going to spend the entire day just doing more practice and stuff after we take questions on these.